Hello everybody, welcome to Abu Smart YouTube channel. Today we see that the rotational dynamics and Newton's law of universal gravitation. Under this topic or under this section, we see that the moment of inertia or rotational inertia, rotational force torque, rotational kinetic energy, and the angular momentum of a body. Under this rotational dynamics, we see that the moment of inertia, rotational kinetic energy, angular momentum, torque, and the work done by the torques. The moment of inertia is the measure of the distribution of the mass of the body related to the axis of rotation. If the object can be rotated on a distance from the point, you can be measure that the manner or the distribution of this mass of a body related to the axis of a rotation. Let's see that if you take that the body can be upward or a point mass can be upward there at a distance from some point distance r. At this distance r, if you can have a point mass, take that this one is a mass, pointed mass at here, the measuring of the distribution of the mass or the manner of a mass as this axis of rotation is called the moment of inertia. The moment of inertia. So the moment of inertia is depend on the mass of the bodies, and it can depend on the shape and the size of the bodies, and the axis at which the object can be rotated. Mathematically, you can find that the moment of inertia of a point mass which can be pointed at a distance r, the moment of inertia of a point mass which can be rotating at distance r, you get that mathematically the moment of inertia of a point mass which can be pointed at distance r is given by the mass of the body times the distance r squared. For several masses which can be pointed at some distance r, masses of the body m1, m2, m3 up to mn, if they can be pointed over the distance of the distance r1, pointed mass 1, or distance r1, mass 2 can be pointed or pointed at distance r2, and the mass 3 is pointed as r3, and the nth mass can be pointed on rns. You can find the total moment of inertia for these several point masses. In that case, you can get that the total or the net moment of inertia, or in, which is equals to a moment of inertia of a mass 1 plus the moment of inertia of mass 2 plus the moment of inertia of mass 3 plus the moment of inertia of n's mass or n's object. In these cases, you can get that the total moment of inertia, which is equals to, you know that the moment of inertia of one point mass is mass times distance at which it can be rotated squared. In that cases, for the moment of inertia 1, you get that mass 1 times distance 1 squared, mass 1 distance 1 squared, plus for the second masses you get that mass 2 distance 2 squared, plus for the third masses you get that mass 3 distance 3 squared, plus then up to the nth point mass, that is mass n distance n is squared, distance n is squared. This is if the point masses are if there are several point masses at several distances, you get the total moment of inertia of the bodies by this. If you can be use the geometric series, you can be indicating this expression, or you can take that the total point masses moment of inertia is the summation of the mass and the radius I squared when I is from the first point mass up to the nth point mass, you can be get totally this expression in case of the geometrical representation as the summation of masses and distances scaled. And another is the rotational kinetic energy of a body. Next to this one, we can see that the rotational kinetic energy of a body. Rotational kinetic energy of a body. It is the kinetic energy of a body when the body of a moment of inertia I rotates on the axis of rotation by the angular speeds. You can begin that rotational kinetic energy of a body is a kinetic energy by which the moment of a point which have a moment of inertia I is rotated or moved at the angular velocity of a body. You know that in case of the linear motion, our kinetic energy of a body is half times mass times the speed scale. And you can be represent this equation by half times mass times. You know that in case of the rotational motion or rotational kinematics, the tangential velocity is given by radius or distance at which can be rotated times the angular displacement. If you replace this equation for tangential velocity in case of the equation of kinetic energy, you get that radius at which the object rotates times angular velocity joule scale. This expression gives us that half mass times radius scale angular velocity scale. But we know that the moment of inertia of a point mass is given by mass times the distance at which the object can be rotated scale. You know that moment of inertia is mass times the distance at which the object rotates. Then you can be replacing in case of this one half of this is the moment of inertia of the body, moment of inertia times angular velocity scale, the rotational kinetic energy. Because the rotational kinetic energy is the energy by which a body of moment of inertia can be rotated at the rotational curve or at the circular curve by the angular velocity. So the kinetic energy rotational is given as half of the moment of inertia of a body times the angular velocity scale. Since it is a form of energy, its SI unit is joule. In case of the linear motion, you know that the kinetic energy of a body depends on the speed or the velocity of a body, and this rotational dynamics also, the rotational kinetic energy depends on the angular velocity of the object. If the angular velocity of the object increases, the rotational kinetic energy of a body also increased. Take that, if the angular velocity of a body is doubled, for example, you get that the rotational kinetic energy can be increased by 4, since it is scaled. If the angular rotational velocity is doubled, you can be get that the value of the rotational kinetic energy can be increases by 4. The other one or the third one is the torque. Its linear equivalent is a force. Torque of a body if object can be rotating on a curved path at a distance r. And in this case, objects which can be rotated on this one can be have a tangential velocity. Let's see that the force which can be causes the acceleration. Now in rotational, the force is the rotational force or torque. If you apply a force here, you can easily open the door. Here is the point that the object rotates or the axis of rotation, that is a radius of the body or at which object rotates. The force that you apply here is perpendicular to the radius or the axis of the rotation. If you apply force here, you cannot easily open the door because it is a rotational motion. Mathematically, you can be expressed that torque is the force times the perpendicular distance at which the object rotates. It is a vector quantity. Its direction is along the direction of the angular acceleration. From second Newton's law of motion, we know that the force which can be act on one body is directly proportional to the mass and the acceleration of the bodies. In these cases, its linear equivalent is force, but in rotation we have a torque. You can be expressed that torque, which is equals to the mass, can be equivalent in rotational dynamics with inertia. Inertia times acceleration can be the angular acceleration. When the unbalanced torque can be act on the body rotating on the curve, it can be caused to change its angular momentum. If you take that the unbalanced torque or the unbalanced net torque acting on a body which can be rotated on the curved path, in that case it can be caused to change the angular momentum of the bodies. Linearly, we know that the linear momentum, which is equals to mass of the bodies times the velocity of the bodies. Since it is a rotational, our angular momentum can be represented by, you can be translated that the rotational equivalent of mass is moment of inertia times the rotational equivalent of velocity is angular velocity times angular velocities. And you can be get that the SI unit or the units for angular momentum from this expression. You know that the SI unit for moment of inertia is kilogram meter squared, and the SI unit for angular momentum is radian per second. You can go to that radian per second. So for angular momentum, you can get that the kilogram meter squared per second is the unit for angular momentums. The measurement of radian is equals to 1. Angular displacement is equal with the tangential distance over the distance at which the object can be rotated. Since both of them are distances, here you can be get that meter, here you can get meter by meter, you can be get the units for angular displacement, a radian, in this radian which is equals to 1. Every mass in the universe can be attracted by another mass in the universe by the force which is the attraction gravitational force, which directly proportional to those masses and inversely proportional to the scale of the distance between them. If you take that in the universe, take that here at a distance r, you can be get that the two masses, if this one is mass 1 and take this one as mass 2, if you take that two masses, mass 1 and mass 2, they can be aparted by the distance r. There is a force which can be attract them to each other, a force which we call it the gravitational attraction force. This gravitational attraction force can be according to this law, when there is two masses in the universe, the force which can be attract them to each other is called the gravitational attraction force. It can be represented equal with the gravitational constant g and the product of two masses over the scale of distance between them, where g is the gravitational constant, which is equals to 6.67 times 10 raised to minus 11 Newton meter squared per kilogram squared. This is an experimental number which can be getted as a constant number, or you can be say that the Newton's constant or gravitational constants. For example, if you take that as this distance the planet can have, take that the planet as Earth, as this distance the Earth can have a satellite, here as this point is or as a distance from the Earth, at this distance the Earth or the planets have a satellite. If you can take the Earth planet at this distance, it have a satellite. Here, if there is a satellite, there is a force which can be between these two massive objects, Earth and the satellite, to attract them each other. That is called a gravitational attraction force. You know that the mass of Earth is there, mass of Earth, and the satellite can also have mass of a satellite, and there is a distance between them. In this case, you can get that the attraction gravitational force between this Earth planet and its satellites by the expression you got that the gravitational force which is equals to, or the attraction force which is equals to the gravitational constant times mass of the Earth, mass of the satellites over the distance between them scaled, the scale of distance between them. And another one is if the satellite can be out of the radius of the Earth, if you take that, a satellite can be occurred here, you can get that, or out of the radius of the Earth, this one is the radius of the Earth. If it is out here, if you can get another satellite, our Earth surface have many satellites, but naturally there is only one satellite that is small. There is another man-made satellite. If you can take out part of the radius of the Earth, if you get here the satellite, and this outer part you can have a distance that is, or you can say that a distance h, or the distance that can be above the radius of the Earth. In these cases, you can get that the gravitational force between the Earth and the satellite at a distance from out or above the radius of the Earth. You can be using that the gravitational force that which can be above the Earth's surface. Above the Earth's surface is given as the gravitational constant G times mass of the Earth, mass of the satellite over the distance between them scaled is. Since it is above the radius of the Earth, you can get that the total distance here, which is equals to total distance is radius of the Earth plus the distance that is above the Earth. You get that the radius of the Earth plus the outer part distance or the Earth's scale. Kepler's law of planetary motion. Johannes Kepler can have delivered 3 laws in case of this the planetary motions. Now, it is the experimental law which can be described that the movement of the planets around the sun, the motion of the planets around the sun. That means the motion is a rotational motion. Take this a universe and a sun. Here we can have a sun. Planets can be rotated around the sun. In these cases, Johannes Kepler can be delivered 3 laws. First law states that the planets in the universe can be rotated around the sun in an elliptical path at one focus. It's the Kepler's law of planetary motions. In his first law, Kepler states that the planets which can be orbited the sun can orbit the sun at the elliptical path at one focus. If you take the planet here at average distance a, it can be orbiting the sun on the elliptical path on one focus point only. This is the first law of planetary motion, which can be stated by Johannes Kepler. The second law states the line joining from the planets to the sun can be crosses equal time in equal areas. If you take the planets, a line joining from the planet to the sun can be traveled in equal time interval in equal time. An elliptical path, or it is ellipse. The second law states that Johannes Kepler stated in his second law, the line joining from the planets to the sun can be crosses equal time interval in equal areas. If you can take another line joining from the sun to the planet here, areas. Now you get that in second law, the time 1 which is equals to time 2, or you can say that area 1 is equals to area 2. And it is third law, the Kepler can state that experimentally there is the period that the planet takes to rotate the sun. If you take here as this one focal point, you can get that one planet. This planet can take a duration or a time that it can be rotated to the sun. If the planet can be a planet at this orbital point or at this elliptical path, if you take the planet is the Earth can be orbited to the sun in a period of time that can be taken. If the planet is the Earth, it takes a period or a duration to be orbited to the sun. The duration that it can be taken in this orbited to the sun is called the period or a time t. If you take the Earth's surface or Earth's planet can be orbited to the sun in 1 year, so that is called the period. According to the third law, Johannes Kepler can be explained that, or it can be described that there is the relation between the period and the average distance between. There is a relation between the period or a duration that the planet can takes to orbit the sun and the distance between the sun and the orbit, that is the average distances. Now, in third law, Johannes Kepler can be described that this period is proportion with the average distance by the value of the square of the period is directly proportional to the cube of the average distance between the sun and the planets. The third law can state that there is a duration or a time that it takes while the planets can be orbited to the sun. This is related as the period scale, or the time that they can be taken to orbit the sun scale is directly proportional to the cube of average distance between the planet and the sun. If you take there is a distance between the planet and the sun, this distance is average distance. Take that average distance as average distance, and you can express this one. It represents that the scale time ratio with the cubic average distance can be given Kepler's constant. The Kepler constant, that Kepler constant is equal with 4 pi squared over the gravitational constant and the mass of the sun. You take that period scale over the average distance between the sun and the planet can be equal with the Kepler constant is known 4 pi squared over the gravitational constant and the mass of the sun. Let's prove this equation. You know that when the planet can be orbited the sun, here at this point we can have a force. That force is a force which can be keep the planet at this distance. It is called a centripetal force. A centripetal force which is represented by the mass of the planet speed scale over the distance, and also between these two massive objects, the sun and the planets, there is a force which can be a force between them, the attraction gravitational force between them, that is called gravitational attraction force, which can be represented by the constant gravitational times mass of the planet, mass of the sun over the scale distance between them, at one focus point at this elliptical point, the centripetal force and the gravitational force is the same. Take that, the gravitational force is equal with the centripetal force at one focus point at which the planets can be orbited to the sun. Now you get that from this expression. Listen, the gravitational constant, mass of the planet, mass of the sun over the scale distance between them is equal with the centripetal force. The centripetal force is a force which can be keeps the planets on this orbit. So mass of the planet times the scale velocity over radius. You get that the mass of the planet, the scale velocity over the distance between them. But we know that. The speed scale or the speed is represented by the radius. That means the distance between the sun and the planet, and the angular velocity by which the planet can be orbited the sun. If you scale this one, you get that v squared is equals to radius squared over omega squared. And also here you can be get that mass of the planet can go out with mass of the planet. Here, since we have a distance scale, one distance can be go out with the distance, and finally we get that the gravitational constant, mass of the sun over distance, which is equals to the speed scale, v scale, which is equals to distance between them scale times the angular velocity by which the planets can orbit the sun. In case of this, you get that the gravitational constant over mass times mass of the sun over the distance, which is equals to distance scale times the angular velocity by which the planets can orbit the sun. But if you can take the rotational kinematics or rotational motions, when the planet can start orbiting the sun from here, and it can be rotating on the elliptical path to be complete one orbital motion or one complete motion, you know that the angular displacement theta, which is equals to 2 pi radian, or it is 1 revolution. And also in these cases, while the planet can be orbited this elliptical path for 1 revolution, it can be take that the period t, or a time of rotation. That is, a time of rotation is called the period t. From this, we get that the angular velocity by which the planet can be rotating the sun for 1 revolution, or for 1 complete path, you can be get that 2 pi over the period t. 2 pi over the period t. Let's substitute in case of the angular velocity of the planet by this value. Now we get that the gravitational constant, the mass of the sun over the distance, which is equals to distance scaled, and for 1 complete or for 1 rotation, our angular velocity by which the planet can be orbit the sun is 2 pi over the period t, then scale it. You get that the gravitational constant, mass of the sun over the distance, which is equals to distance scaled. If you are scaled to 4 times, if you have scaled pi scaled over time scaled. Now you get that gravitational constant g, mass over the distance is equals to the radius scaled or the distance scaled times 4 pi squared over time squared. You can be cross it and you get that gravitational constant times mass of session times the time squared is equals to distance times distance squared is distance cube times 4 pi squared. Here you get that to be, let's find is that the period or the time squared is equals to divide both sides by the gravitational and mass of the sun. You get that 4 pi squared, the distance between the sun and the planet cube over the constant g times mass of the sun. You know that here this is the Kepler constants. You get that the time squared over the distance between the planet and the sun cube can be given for you the Kepler constants. Kepler's constant, that means the Kepler constant is equal with 4 pi squared over the gravitational constant g times the mass of the sun. So now our research law is proved. Geostationary satellites are satellites that orbit the Earth at equator by the same angular velocity of the Earth. Geostationary satellites. Geostationary satellites are satellites which can be orbited around the Earth's equator with the same angular velocity of the Earth. Now, the satellite can be orbited around the equator of the Earth's surface with the same as the angular velocity of the Earth around the equator of the Earth's planet. There is a force which is centered the satellites to the center of the Earth, that is centripetal force, which causes the centripetal acceleration, and a force which can backtrack the satellites to Earth's planet is called a gravitational attraction force. They can be orbited the Earth by the angular velocities. So those satellites can be geostationary satellites if they can be orbited the Earth at equator by the same angular velocities with the Earth. Under this topic, we can see that the two velocities of the satellites. The first one is the orbital velocity, and the escape velocity. Orbital velocity is the speed of the satellites when they can be orbited around the Earth. Geostationary satellites or satellites can have the orbital velocities. In that case, you can be take that the distance between the Earth and the satellite. If it can be at the radius of the Earth, you can be take the radius of the Earth. But if it is in outer part or above the Earth's surface or Earth's radius, you can be take that the distance between the Earth and the satellite. If you can be take here a satellite, you have above the radius of the Earth, you have a distance or some distance. In that case, you can be take that the total distances between the satellite and the Earth. Now, to be find that the orbital velocity, since it is the speed of the satellite by which the satellites can be moving around the Earth or moving around the planet, you get that there is a centripetal force of satellites which can be centered, or because of the centripetal acceleration of the satellite, you can have that centripetal force which is mass of that satellite times the speed squared over the distance between the Earth and the satellite. Between two objects, that means between the Earth and the satellite, here we can have the mass of a satellite and the mass of the Earth. Between two masses, we have a gravitational attraction force which is directly proportional to the product of two masses, mass of the Earth and the mass of the Sun, satellite, over the scale distance between them. At this point, our orbital velocity is the velocity by which the satellites can be moving around this orbit or around the Sun. In that case, at focal point or at one focus point, you get that the centripetal force and the force which can be between Earth and the satellite can be the same. Take that the force, gravitational force or attraction between the mass and the satellite is the same with the centripetal force of satellite. In that case, you can get that the orbital velocity or the velocity by which the object can be moving around the Sun. That means here in case of the tangential velocity that we can be have here is the velocity by which the satellite can be moving around the Sun. So constant gravitational mass of the Earth, mass of the satellite over the distance between them is the same as the mass of the satellite, the orbital scaled velocity over the distance of the bodies. You get that from here. Mass of a satellite can be out, one distance can be got. You get the gravitational constant mass of the Earth over a distance which is the same as the scaled velocity. To get this velocity or this orbital velocity, v scaled is equals to the gravitational constant mass of the Earth over the distance. So our velocity or orbital velocity is equals to radical constant gravitational mass of the Earth over the distance. This is the orbital velocity or the velocity by which the satellite can be moving or orbiting around the Earth. Okay, the next one is the escape velocity of the satellite. Take that if the satellite can be launched out from the Earth's planet, you get that if it can be launched out, if the satellite can be launched out, it will able to climb out that the potential of the Earth at final. In that case, you know that the potential energy can be given as minus the constant gravitational mass of the Earth, mass of the satellite over the distance between them. If the satellite can be launched out, it will able to climb out that the maximum potential of the Earth is a summation of kinetic energy and potential energy is 0, means that the kinetic energy of the body is equals to the potential energies. In this case, we know that the kinetic energy can be represented as half of mass times velocity squared, which is equals to, since we can have the potential of the Earth or the potential energy is the constant gravitation mass of the satellite, mass of the Earth over the distance between them. We can have mass of satellite can be got with mass of satellite. If the satellite can be launched out from here, its kinetic energy is depend on the speed, that is the speed. Since mass is constant, you get that here half of the speed by which the satellite can be launched out as equals to the gravitational constant mass of the Earth over the distance between them. Now you get that the speed scale is equals to twice of the constant gravitational over mass of the Earth over the distance between them. you get that the velocity which is equals to and radical of twice of the constant gravitational and the mass of this over the radius. This speed is the escape velocity or the speed by which the satellite can be launched out and reaches or climbs out the maximum potential of the Earth. So this one is the escape velocity. That means the velocity by which the satellite can be launched out and reach the maximum potential of the Earth. From these equations, you can be see that the orbital velocity of a satellite is independent of the mass of that satellite. Let's see that the end of the unit equation, equation number 8. It says that this system is in equilibrium. It says that the system is in equilibrium. The vector B can be projected at an angle of 30 degrees in the negative x directions, and vector R can be projected at an angle of 60 degrees in this way. It can be said that if the system is in equilibrium, find the relation between the three vectors. It says that vector P and R and also vector W. The relation between them while the system can be in equilibrium. Let's see that here we can have a y direction. Let's take that the vector are in its two components. The first component is the horizontal component of vector R, that means Rx, and also the next one is Ry, or it is vertical components. The system is in equilibrium means that the net force which can be act on the object is zero. To be get the equilibrium positions, we have a criteria that is the net force in all components must be zero. That means the net force in horizontal component and the net force in vertical component also zero. If you take that the net force in horizontal component, you have horizontal component Rx or vertical Rx, and also here we have the Py, that means vertical component of vector P, and also here there is a Px, that means the horizontal component of vector P. You take the summation of forces in case of the horizontal component must be zero to be the object or the system is in equilibrium. You can be get that the horizontal component of vector R, that means R times cosine of 60 degree, and the vertical component of vector R means that R times sine of 60 degree. And also here for vector B there are two components. It is vertical component can be vector P times sine of 30 degree, and it is horizontal component is a vector B times cosine of 30 degree. Let's take the system is in equilibrium. That means to be that the system is in equilibrium, the summation or a net force which can be acting all components must be zero. If you take that the horizontal components for two vectors, you can have the R cos 60 degree plus P cos 30 degree. We know that the value of a sine of 30 degree, which is equals to half, or you can say that 1/2, and cosine of 30 degree is 0.866, or you can say that root 3 over 2. Here we can have a vector r cosine of 60 degree, means that cosine of 60 degree is equal with the sine of 30 degree, that means half times 1 over 2 plus p times cosine of 30 degree, means that root 3 over 2 times root 3 over 2. Then from this expression you can begin that which is equals to 0, since the summation as this component must be 0. Now you know that the p vector in its horizontal component in the negative x direction, so you make it negative. That means r half of r vector minus root 3 over 2 of p vector, which is equals to 0. You get that the r vector, which is equals to root 3 vector p. The relation between two vectors is this one. Let's see the y component. Since the system is in equilibrium, in y component we can have a negative w here. That means here in this case we can have a vector w. Since is a negative in the negative directions, the summation of the y component net force can be given for you a w. Then you can be take that y component have 2, so w vector component minus or plus the net force in this direction is that is minus w, which is equals to give 0. Now you get that summation of fy, which is equals to, in y components we can have that p sine 30 degree plus r sine of 60 degree, which is equals to here the two component summation can be given for you the y, to be that the system is in equilibrium, since we can have here the negative w now, which is equals to the then p times sine of 30 degree is 1 over 2 plus sine of 60 degree is root 3 over 2, which is equals to the summation in y components, in positive y components, which is equals to sine of 30 degrees half of p plus sine of 60 degrees root 3 over 2 times r, which is equals to w. Then you get that 1 over 2 p plus root 3 over 2 times r, means that root 3 p, which is equals to w. In case of r we have root 3p. Then 1 over 2 of p plus root 3 times root 3 is 3p over 2, which is equals to w. Then you can have guessed that p plus 3p is 4p over 2, which is equals to w. Then 2p is equals to w. Now the system is in equilibrium, and you can repeat that the relation between the vectors as r, which is equals to root 3p, and the w, which is equals to 2 times p.